let's start. Today we are having Alessandro Ingrosso. Alessandro is now just joined in September, October.
Yeah, September.
Radboud University, so he moved to the Netherlands from Italy. And before, so he did a PhD with Riccardo Zecchino in Torino, then another postdoc in Colombia with Larry Abbott, and then another postdoc in ACTP as a postdoc fellow, and then he came here. So yes, so let's let you start. Sorry, and just to tell you, the crowd is there. It's very broad, let's say. So there are some with statistical background and some machine learning and some mathematician and some more like psychology, quantitative psychology. So it's really broad.
Okay, so I prepared like 30 minutes, but this can go up to 1 hour if you have questions. So if you like me, ask questions. If you don't like me, then don't ask questions. It will be over in 30 minutes. Okay. And thanks, Clelia, for inviting me. It's actually the very first time that I come to Amsterdam. I need to take some time to visit around. So this is a recently started line of work that basically was started by Federica Gerasci, who's now in Bologna, and comes from a collaboration with these two people that are in Italy, University of Parma, and particularly Pietro, who developed sort of some kind of generalization of the kernel renormalization method that Sompolinski introduced in a PRX paper in 2018, if some of you know. But I'll tell you more about this. Which I think is some sort of a revolution in the usual way in which statistical physicists think in terms of learning. Usually you average over the data, but Sompolinski introduced this kind of new way of thinking in terms of kernels, which were sort of forgotten in the context of statistical mechanics. There was this Manfred Opper, who's a very, very big name, who sort of introduced the field to this, but then sort of faded away. So, and this talk is going to be about transfer learning. For the people who don't know what transfer learning is, like me, 8 or 9 months ago, it's a very convenient way of teaching, which is basically like instead of teaching a student, you cut the student's brain and then replace at least a part of it with a brain that already knows stuff. In deep learning lingo, it means that you have a very big neural network and a very big, say, a very large data set, so you're not prone to overfit, and you can actually learn some interesting features. And then you train this network on a usual task, say this is an ImageNet task, for instance. Then what you do is take the weights on the trained network and transfer, not necessarily all of them, onto a student network, I'm going to call it, or let's say a target network. And the main problem here is that you don't have enough data, so you have a way smaller data set, and so you're prone to overfit. So these weights will give you a good prior on the feature that have been learned anyhow on a completely different task. So for the purposes of this talk, I'm going to call this the source task and the other the prone to overfit model task. And it's not a chance that these are sort of medical images, because this is a typical problem in medical imaging, medical diagnosis, with deep learning methods, because we don't have enough patients, we don't have enough data. Say in echographies, we have kind of like 1,000 echographies, and you're prone to overfit because you have the entire video of echography for a single person. So you have to rely on some ImageNet trained data network. So some phenomena. There are like 1,000 papers on transfer learning. And nowadays, you guys know that you can't really retrain ChatGPT from scratch. So you do LoRa on top of it. So you fine tune this kind of stuff. So it's very popular nowadays. I'm going to tell you about some phenomena, especially in the field of medical imaging. So the idea is that you have a source task, which can be ImageNet, and then you want to solve this problem, which is a breast cancer detection task, where you have benign or malignant tissue, okay? So you train a ResNet, for instance, with 18 or 28 layers, or you just download it from a PyTorch website. And then you can either retrain it or just use it and train just the last layer, which is the decoded layer, to solve this problem when it's presented with this input, maybe reshaping the. So what these people did in this very interesting paper is that they try and understand how the complexity of the input structure is represented in sort of a hierarchical feature at the level of transfer. And that's what they call layer-wise deep transfer. So you can sort of transfer up to a certain layer and then retrain, or you can transfer the whole network, okay? And so, for instance, this is the main result. Here you have a network which is trained on this task, possibly retraining from here onwards. So you transfer up to this layer. I don't know if you guys can see. So you transfer up to these layers, so you freeze these layers, and then you retrain from here onwards. Okay. Oh, I cannot touch.
Yeah.
And so as you can see, it's not like a flat curve, but it has a maximum. So it's like, it's best if you just freeze all these layers, you transfer up to the 13th layer, and then you retrain.
And is this for sort of a fixed number of flops?
Fixed
So you
number.
say I get to do this many hours on the GPU.
Yeah.
Okay.
You over optimize. Yes. You maybe you do other parameter optimization.
Right.
Yeah.
Because otherwise you would think, I guess, that starting from 0 would yield the best results.
This is starting from 0.
But if you
Well, the best. I mean, you're always gonna fit on this because you don't have enough data.
So this is like validation. That's the set.
This is test. Yeah. Always test good. Yes. And as you can see here, this depends actually on train sizes related to what you were saying. So like this peak moves on the left, the more data you have. I mean, it's not, you can see it very nicely there, but it seems like that the more data you have, then it moves on the left. And the limit in which is the limit in which like the specific feature of the data at hand can actually be found because you have enough data. But here, when you don't have enough data, your peak is like moving on the right.
It seems like the peak is actually in the same place, no? The peak doesn't move, it's just that the lower ones get better.
Well, the relative here is like 0 is here. It's like
Okay.
slightly moving on the left. Okay. But it's getting flatter and flatter. Okay, so this is like you take this guy and then you transfer it here. What you can do is you take, for instance, this guy and try to transfer it to itself by degrading it. So like, for instance, you can say you want to start cipher. So you can transfer cipher to cipher itself, say, if you don't have enough. This is like a nice way of theoretically studying it. Or you can understand what are the main features which are transferred from the source to the target. So the game they played here was that they constructed some clones of cipher. They trained on these clones and then tested on cipher again with the same idea. So like ISO-GM means I take the whole cipher, I have 10 categories. For each category, I construct an effective generality model, which can only contain, for instance, the mean of that ball, okay, like an IID ball, or I can keep the mean and the entire covariance matrix. So these are the images in this ISO-GM. For each class, you have the same mean. These are the images for the GM, which is for each label, I can generate an image with the same mean and the same covariance matrix, but all the higher order cumulants are set to 0. So it's an effective Gaussian mixture model. So you train on these guys, and then you do the layer-wise deep transfer on normal cipher. And what you see is that here, the peak is here, but the peaks move now on the right. That means that the more Gaussian feature I see in the data, the more I can sort of reuse features that have been actually found by the source network. Is that clear?
Why is the first one not completely flat? The leftmost plot, because you're saying
you need a deep network.
The target are the same.
You need a deep. No. You need a deep network, right? This is a deep network trained on this guy, which is just a bunch of bolts in this n-dimensional space.
Okay.
And so you train on this, and then you transfer on cipher. So it makes sense that you have to retrain from scratch
Because
you didn't learn anything.
It's so boring that it didn't really know.
Yeah. You just learn the mean, but the mean is not enough to actually generalize. But here, actually, you learn the mean and the covariances of your data set. And so they and since you can go up to the 20th layer, and you still can see some interesting information about your dataset, which is just like mean and average, mean and covariance matrices. So the second moment sort of gets projected onto here, and then if you do it like if you train an autoencoder and then you test it, sort of you transfer it to the entire cipher, then you can just retrain the last layer. That means the peak is the last. So you just retrain the last layer, you use the whole feature which have been trained on the autoencoder stuff.
And what if you don't retrain anything?
Yeah, no, okay. It can be that like, yeah, this I'm not sure they actually test it. I mean, in general, it's not even possible because you may have, like in this case, you have 10 categories versus 2 categories. But in this case, maybe they tried. I should ask.
Can you just comment on this, like the similarity and the difference between this transfer learning framework and the complete and incomplete data set, like back to the 80s, the teacher student setting, and then you can get the complete set of input or incomplete set. I saw that because you have the source and the data class where it like in the source you have more.
It will be formalized and become more clear. But this up to now is not a teacher student setting, it's like a Gaussian mixture setting.
Okay.
So the output is given by exactly it's a deterministic function of which ball I give you. Okay, there's no teacher here. The teacher, like we're using an explicit, so they are using an explicit data set. Then you can sort of modify the data set, but the labels are still there. They're not given by a function, which is the teacher. I will show a teacher-student setting, which is called a hidden manifold model later.
What about the last picture on the right?
The last picture, so you train an autoencoder to give you images. You sample from this autoencoder. You train ResNet, and then you transfer the ResNet onto another one on Cipher. And so this is telling you that the features trained on the autoencoder are basically the same as Cipher, even though the images are not the same, but the autoencoder captured all the higher order humans in the single images. So we want to make some theory for this, and yeah, like going back to the 80s, but the theory that we had was just some theory from a single layer case. So you can do everything, sort of almost everything you want on the perceptron, on regressions in a high dimensional setting. There's a lot of work by the group by Cengiz, Belevan, Lenka, you name it, Montanari, of course. And so I'm just going to present this example, which is an example of a teacher student. So here you have a low dimensional input, which is represented by, so I don't know if you can see it, but it's like a lower dimensional representation called C, which gets projected to what you actually observe called X. And then the main point of this so-called correlated hidden manifold model is that the output is given by a teacher vector. So you have a teacher, which is represented by just a perceptron, gives you the label. But the inputs that you see are expression over lower dimensional representation, and the labels are given by these lower dimensional representation, not from the higher dimensional one.
So we're going right to left.
You're going from here to here, from the label, yes. And so what you can do is that then you construct like another effective teacher, which is this guy. So you have a teacher for the source and a teacher for the target. And then you can control, I'll say way more on this later, you can control the similarity between the teachers or the similarity between these projections from the lower dimension to the higher dimensional thing. And so you have a teacher-student setting in which you sort of can control the output and also the similarity between the inputs. Yes.
Do you have similarity? Do you mean the similarity in the architecture of teacher or the way?
The teacher is just a vector, so you can take two vectors and control the angle. And this projection is a matrix, and again, you can control the angles between the rows of the matrix. Okay, but I'll be more precise later. I just want to give you some knowledge of this. So what they did was they trained a one hidden layer network. Let's call this first and second layer WS and BS. And then you take WS and put it here, and then you just retrain the second. Okay, this is just like the simplest case of transfer learning, which you retrain the decoder. What they did what they did in this paper.
Double tap on it. Yes.
Okay, what they did in this paper was they show us, I don't know how to get rid now.
You can press the minus thing, it should disappear.
You can move it also.
So the main story of this paper is that we have a theory for this guy because it's just a perception problem. So you can work out the theory for this because you can just sort of compute what the system is seeing at this level. So you just compute the covariance matrix of the feature at this level and you use so-called Gaussian equivalence to compute the feature, the target error, generalization error at this level. But the main message of this paper is that this is a good model to actually represent what happens in the reality. You see that this is real data with MNIST, and this is what happens in a correlated hidden manifold model. You could tweak the parameters a little bit to get something which resembles what you observe in the reality. And now focus on the difference between the blue curves and the orange curve. Orange curve is random features. So these WSs are completely random. And the blue ones are the transfer ones. So transfer learning is always better than random feature. So it's always better to actually transfer this guy up to this guy when you have some similarity between these two. Okay. It is a function of this similarity and also a function of this similarity. I'll show you later. And then look at the green one, which is the two-layer case in which you actually train both VT and WT again. And you don't do always better in transfer learning. There's a crossover at some point between the green and the blue curve. But if you don't have enough data, then transferring is always better because you're going to overfit. So transferring is good if you have some sort of similarity between the source and the target task, and if you don't have enough data. This is not always. So they also show, okay, this is just saying the same thing that I said. They also show like as a function of this similarity. So this parameter Q controls the similarity between the overlap between the t-shirt vectors. They're just vectors. You can plot like the error as a function of the angle. And P is the number of patterns, and 1 is the number of neurons in the hidden layer. So more data on this side and more similarity on this side, okay? As you can see, it's always better to transfer when you don't have enough data and then when the source task is close to the t-shirt task, to the target task. And here you see the difference between transfer learning and random features learning. And you see it's always better to retrain, always better to actually train the first layer, but not always. You have these so-called negative transfer effects, which are kind of, I don't know, strange to me. It means that if you transfer something that has been overfit on a source task, it's better to just drop it and just take random features, okay?
It kind of makes sense, no?
Yeah, it kind of makes sense.
The network randomly, it's not with some very specific.
The thing is, the P of the source is very high. So it's not like overfitting. I don't know, maybe it makes sense, yes. Now it's the 10th time that I think about it, and maybe it makes sense, yes. By the way, this is an effect that is called negative transfer in the literature. So we wanted to have a theory for what's happening here when you also train the first layer, okay? Yes?
I'm not so used to thinking these terms, so I just need some clarification. So the P over N1, so the pattern, P is the number of patterns.
Yes, I
And
think I have
an optimal.
So, yeah. Yeah, P is the number of patterns over neurons on the first layer.
Yeah. So for adding more and more patterns, you have kind of an optimal choice of the number of neurons that you want.
No.
In the next next slide, you have like this.
Yeah, this is a function of the ratio. Yes, but what's the optimal you're referring to?
So wait, I'm confused.
So when you scale up, the network, you scale up the number of patterns.
Yeah.
This is the usual scaling. Yes.
So the leftmost plot here says actually there's quite a large range around this P over N of 1 in the middle.
Yes.
For which it's a bad idea to transfer.
Yes.
Or regardless of how similar your source and target.
Yeah.
That's not surprising, no?
This part is surprising to me.
Yeah.
Yes.
Yeah.
That I don't understand. But I didn't redo the simulations.
And it gets smaller afterwards.
Yeah. This thing is also like, I don't know. I haven't thought about this fully.
These experiments were done on MNIST, right? Or synthetic?
MNIST, yes. And these are on MNIST.
What is it?
It's like MNIST, but with letters.
Okay.
So, but what it means also that if you have sufficient number of neurons, then you're always happy to train before to.
Sufficient number.
Transfer,
It's a
right?
function of the ratio.
Yeah, but if you have a lot of neurons, then you go down in this plot.
Oh,
it will be like
yeah, this is like the infinite width limit, but in that case, you're not transferring anything. So I'll show you that. If you have enough neurons, it's basically like doing kernel regression. Okay. So these are just some phenomena, and we wanted to have a theory. Our approach was to consider, try and build a theory for the first and the second layer, and possibly for a deep network. Okay. So we called our approach with this very pretentious name, Symbolistas Transparisi. If you guys know something about StatMech, I'll tell you what Transparisi originally is. So StatMech formulation of transfer learning in Bayesian networks. So we're not going to use GD or Adam, but Langevin to train our networks. So it's a Bayesian approach. I'll be more precise. And the idea, we start from a one hidden layer network. So I call S for the source and T for the target. I put theta S and theta T are the joint parameters, and then I want to transfer in some way, represent the transferring of just the first layer, and then train both. So train this guy and this guy, and have a theory for this. How can I represent it? So in a Bayesian setting, the idea is that I can train 1,000,000 times and construct a weight posterior, so a posterior of the weights given by the likelihood, which is e to the minus beta of the loss. So I have a certain likelihood of, as a function of the data set, and the prior of parameters, which can be like the usual Gaussian. And the likelihood is proportional to e to the minus beta, the loss function. And the loss function is the usual MSC. So phi is the output on the network, y is the target. And the network output is the one in the layer network with just, it can be generic here, but you have just a linear output. So a linear, a scalar product between V and sigma of the currents, say, the local field H. And we always are, and this is a very important thing, in the proportional limit, which is P over N1. So if you see Gardner calculation and all these stories, it's always P over N0, which is like the number of units, the number of patterns divided by the input size.
Can you specify what is the choice of sigma here?
Oh, any, yeah, generic. You'll see that it happen. If you can compute the kernel, then you can do for any.
How do you choose beta?
Any beta, yes. And beta going to infinity probably goes to the GD limit, but it's not, it's complicated because it gets a non-equilibrium system.
This again, P, you say number of pair. What do you mean by pair? Is it just a number of classes?
Inputs, number of inputs.
Training points.
Training points, yes.
With number of,
Yeah, like
Size of
MNIST,
data set.
60,000, yes. Size of data set, yes.
but the number of pattern to the source or to the target?
There's going to be a PS and a PT.
Sorry, P is the number of data points.
Number of data
I
points.
thought it was like a measure of amount of number of correlation directions or.
No. Number of data points. Yes, sorry. Yes. So there's going to be a PS and a PT. Let's say the PS is very big.
And this is saturation or near saturation for alpha. So alpha or 1 or.
Alpha is generic, but alpha is order 1. Yes, alpha 0 means that you're in the infinite width limit. I'll tell you later. We cannot really do alpha of order n or alpha of order n0 if n0 is this. It's called the quadratic limit, and it's thought to be way harder than like from the theoretical perspective. So basically, like you have n0 times n1 parameters here, right? But I'm giving you p equal alpha n1. So like you have an infinite amount of information left. So that's why it's called the proportional limit. We usually say alpha 0 is the infinite width limit, in which this is so big that basically you don't learn anything. At least this is kind of a first renormalization the first non-perturbative thing you can do around the infinite width limit. Okay, if the Bayesian setting is clear now, what's the definition of our single instance transparency? It's the following. I hope you see it. So we have a prior on, we have to represent a situation in which we first learn this and then we transfer, okay? So we want to average whatever happens in the training of the target task over the ensemble on the source task. So like in usually say in disorder system theory, you average the log partition function over the realization of the disorder, right? Disorder is uncorrelated. Now here the disorder is strongly correlated because it comes from the distribution, which is the posterior over the source. So you first learn the source, okay, and then you average whatever happens in the target, but you couple WS and WT. In the limit, so gamma equal to 0, for instance, there's no coupling. Whatever happened in the source does not affect the target. Gamma equal to infinity, there's no training of the first layer in the target because WT goes to WS, and so you just learn this guy. But any intermediate gamma means you do what people call fine-tuning. Say you start from an initial condition and then you're allowed to go not far. And how far can you go? Well, it's set by gamma. So like the distance is set by gamma in the very same way in which like beta sets the energy in usual statistical mechanics. So a certain temperature gives you a certain velocity of particles. Certain gamma gives you a certain range of going from the source to the target when you retrain.
Should I think of it a bit like the Lagrange multiplier?
It is
that fixes
exactly. Yes.
the coupling?
Yes. Yes. So you can play around with gamma. And so this guy is a source partition function, which now doesn't depend on the target because it expresses just the fact that the prior on the source is normalized. The source doesn't care about the target, but the target strongly cares about the posterior on the source. Why? Yes.
I just saw your third question because in the answering area you mentioned that beta due to anything, but here you have type 2 temperature system with beta T and beta S. How do you choose it at the end? Or do you take it generally?
Oh, we take beta. I mean, the calculation was done generally, but we take the beta to be the same. In principle, I mean.
So this is the equilibrium model because if beta S equal to beta T.
Well, this guy is in equilibrium. The other guy is not in equilibrium because it's tilted by gamma. So you can wait for equilibrium, but it's a tilted equilibrium distribution, and it's an equilibrium in a tilted Gibbs distribution with the, as you were saying, with the parameter.
Because like Tom Cullen in the 90s, he has a paper with Sherrington considering that model with 2 temperature.
Yes.
And if beta S is different from beta T, this is out of equilibrium. But if beta S equal to beta T, this is the equilibrium model. And now you separate some kind of tilted things by interesting. Okay, I wait for the next slide.
Yeah, no, I know what you're referring to. So they can actually go like get a full RSB or for the SK.
There should be some RSB there.
Yes.
What is RSB?
So why we call it France Parisi? Because what Parisi did with France was like he wanted to study metastable states, so basically non-equilibrium, using an equilibrium formulation. And the idea is that you have 2 systems. One system is described by this sigma, and the other system is the S. So sigma is the target for us, and S is the source. And so you have equilibrium, but tilted by the fact that you need to be close to something which comes from another distribution at equilibrium of S. So S is at equilibrium with its Hamiltonian by B prime is the inverse temperature. And then you have another system which is coupled to this S. So generically, it's kind of a way to sample around the metastable state.
So this is because of the constraint, right? So regularization.
Because of the constraint, yes. It's like gamma is going to infinity there, and there's the delta function.
Can you double tap? Fine.
Yes, okay. So this was originally introduced in the context of spin glasses to understand the relation between non-equilibrium and sort of studying non-equilibrium in an equilibrium way spin glasses. And there's this very interesting paper by Haiping Wang and Kabashima where they use it to understand why learning with binary synapses in a simple perceptron is so hard. It's known to be an NP-hard problem. And it's because of the fact that the typical solutions are isolated. So it's a 1RSB where the typical solution don't have any other solution around. So you can run Monte Carlo until the death of the universe and you will never find an isolated solution. But we use a generalization of this approach, which we called local entropy, in which you can sort of soften this Franz Parisi approach and study the density around a given solution. And that gives you actually non-typical solutions that are attractive with respect to dynamics of usual algorithm. Okay, so like you find non-equilibrium, slightly non-equilibrium, or subdominant solutions. So just to say that this Franz Parisi was introduced in the 90s to study spin glasses, but has been used a lot to understand the structure of the landscape of solution of actual algorithms. And it's connected to entropy SGD, if you know it, and flatness of like flat, so like conditioning of the Asian in dynamics of gradient descent. Okay, so I want to give you a one-slide derivation of this, just to for the ones that have seen replica calculation, because I think this is a kind of a strange kind of replica calculation that I had never seen, because you usually, when you do replicas, if any of you have seen replicas, you sum over sites, you sum over inputs. But here, this is a dual representation. You can think of, say, the KKT and the usual duality in linear system. And then here you have the kernel appears. Okay, so you sum over patterns, sum over inputs. Yes.
I don't get, so we have this N1F and then we have this equation there. Like, what are we doing? I have no idea what we're doing. I just see an equation, but what are we doing?
Good. Thank you. So, so let's say that this term wasn't there, okay? And oh, actually, let's look at this term.
Yeah.
So this is the normalization of the prior.
Yeah, I see this, yeah.
Okay, you take the log of this,
Yes.
and whatever Lagrange multiplier you put in the exponent, you can take the derivative with respect to it and compute.
Okay, so beta, is that what you mean? Okay.
Yeah, for instance, but you can sum whatever else here. Let's say I sum lambda w squared.
Okay.
Okay, then I take the differential with respect to lambda, and that gives me the average of w squared over this prior.
Yeah, but what's, I just want to ask what we're doing. Like,
Okay. Another-
everything with transfer learning.
Yes.
We said like we learn this WS, we transfer to the other one, and then maybe we retrain W like this V. There is
Yes.
no V anymore, and now there's an equation, and I have no idea what we're actually doing
Okay.
because, yeah.
Okay.
So
So V is not there because it's, I mean, I'm thinking, so this is a usual sloppiness of physics. So yes, I'm thinking of integrating over V. V is not interesting in the sense that it's fine. It's not, it's uncoupled. I mean, I'm retraining V here and here. The main coupling is W. The general way of looking at this is a generating function. Okay, this is like a Laplace, if you want, Laplace transform, if you interpret beta of the prior. Okay, so you take this generating function, then you differentiate the generating function to get any moments you want.
yeah, okay, fine.
Okay, so now this is a little bit more complicated cumulant generating function, right? It's a log of a generating function, but it's also average over a prior distribution.
So you consider this as a function of beta S and beta T? Is that-
Beta S, beta T, or possibly any other Lagrange multiplier that I can introduce for free. And then when I take the derivative with that Lagrange multiplier, I can compute averages over this distribution.
Is it correct to say that this big equation is the partition function of the target?
It's average cumulant generating function of the target.
Right.
You see a log of a partition function that it's average again over the prior.
Okay, so you introduce as an analytic tool to compute certain moments.
Exactly.
Okay.
Yes. Yes.
Okay.
You know, I don't know, random magic theory. You know something.
I mean, like, I just want to know what we're doing. We don't need to go to other point.
Okay. Okay.
Okay.
Okay. Analytic function. When I take the differentials, I can compute quantities. So I show you how we compute this thing.
Okay.
So this guy is easy in the sense it's there by itself. And you can write it in say you can do Laplace approximation. Okay, at some point I can write it in a mean field sense, meaning it's our way of saying that we do the Laplace approximation. So you get n e to the n to this say large deviation function, which we call action, and then the main point in the action is this guy here. Okay, and this guy and this guy. And so just look at, so here you see the outputs that you have times this matrix. And this matrix is, you see the inverse of 1 over beta plus k, and k is a kernel.
I'm already lost. I don't know what the Q's are, what the N is, and what it's referring to the whole thing, to just like this Z there, because the arrow is there.
I think the best if we...
I don't see where the Y's come in if you don't have P's.
I think, okay, you
Sorry, but like, yeah, I don't know what you're doing.
Okay. So the best if afterwards I give you a whole derivation on the
I
blackboard.
don't know if someone else has the same problem, or everyone knows where we are.
So maybe the question is, what is exponential n1 over 2s? S is the entire thing.
So,
what is S here?
I have to compute this entire thing.
Mhm.
And I have 1 over zs. So let's first compute zs.
Okay.
So you do a lot of integrals, and at some point you're able to write it in this large deviation form.
Okay, so the exponential is basically zs.
Zs.
Yeah.
Zs is this guy.
Okay.
I compute, this large deviation depends on something that we call order parameters, these qs and q at s, okay? And we need to optimize over. It's like you find, you have a huge thing that lives in a n1 times n0 dimensional space, but they can compress it into just two numbers and optimize over those two numbers. Why do I have to optimize? Because I need to find the saddle point of this action. Meaning I have to I have to find sort of the tipping point of this large deviation function. So it's a function of q and qs. What happens here is that this function depends on some contraction, tensor construction of your dataset and what? Your kernel. This is the average over the prior of the activation function of the on the input mu and the activation function on input nu. So it's a usual kernel that now lives in pattern space. Okay. So if you did kernel regression on this, you will compute this guy, and then you will get exactly this function without the cube. So 1 over beta plus k to the minus 1. You will get this, I don't know what to call it. Say, when you do the average, this is the Stiltius transform, the Cauchy transform.
Mhm.
Okay. So now you have a QS in front. And a QS is self-consistently determined by the fact that it's the optimum on this SS. This thing is called kernel renormalization. So the difference between the infinite width limit, which is n going to infinity, where you just see the kernel, and you compute the output as 1 over beta plus k to the minus 1, here you get this QS in front. QS must be self-consistently determined. So this has been called kernel renormalization, but in the end, it's just saying that you start from an untrained network. If this untrained network is very big, it doesn't learn basically anything, okay? And then you can compute the generalization error just using the prior kernel. What you have to do, if you compress it a little bit, or if you keep it big, but you also increase the number of inputs, then you get this quantity here, this QS, which is sort of changing effectively the priors, changing the effective prior. Okay, so you get that, I don't know, if you use kernel methods, you could in principle optimize over hyperparameters. This is an optimization over the scale of the kernel. So the kernel changes a little bit, but in a trivial way. It just gets scaled. It has an infinite number of parameters, right? It lives in this p times p space, but it's just one parameter that captures what happens during learning.
Just to clarify the last line, so
Yes.
is this sigma h mu sigma h nu is from the target rate?
From the target, yes.
Yeah, and another,
I mean, this is from the source of the target is the same, yes.
and another question is under what assumption you can assume that the output of the source, so the ys is Gaussian.
The main point here is that I'll be more precise later, but it comes from a Gaussian distribution of this h, which is w scalar x. Yes.
No, this is Gaussian for the h. I understand, but what assumption gives you the validity of your calculation that the y is also Gaussian?
No. Y is a vector, just any vector. This I'm
Any
not
vector.
averaging over the data.
Okay, so y
No
is
average. No.
Gaussian. Okay, thank
Yes.
you.
Okay. Are you content? Good. So I do something which is even worse now for you, which is now I have to do a log. Now I need to compute the log, and whenever a statistical physicist sees a log, immediately thinks of limit of the derivative of z to the n. Okay, this is why Parisi got the Nobel Prize. Actually, no. I mean, Edwards came up with this, but then Parisi sort of perfected it. This is called the replica method. Ideally, it's just a way of, say, computing a log just by the fact that so z to the n is e to the n log z, so 1 plus n log z. Take the differential with respect to n and you get the log, right? So now, but n is going to 0. The main point of replica method is that you take n to be a natural number, you do the calculation on natural numbers, and then you say, okay, now I'll take this to go to 0, not caring and just assuming that this you can do this continuity, okay? So that means that this z to the n, so this whole thing is z, I have to replicate it n times. So basically I have to, now I have a single source because the source is not replicated. The log gives me z to the n, so it gives me this guy n times. So I need to replicate n times the target network. It's
Do you
just
think the whole thing is z, or is it only the part that comes after the log?
this one.
Yeah, okay.
So I'm averaging this guy, which is singular, but then this thing, the log becomes z to the n, and then afterwards I'll take n to 0. So I lied to you. It's a two-slide derivation. So I took the same from before, and then I turned it over because I'm going to integrate over the first layer first, okay? So if we take the prior on the first layer to be Gaussian, whatever inputs I have, without averaging, then the currents, the local field, the W times H will be Gaussian, okay? So, but in this replicated space. So I define H as rescaled W scalar X, yes?
I have one question. You started with Bayesian neural network, but then now it's a fully connected network. So
Yeah, it is a fully connected, but it's Bayesian. I'm considering the posterior over.
okay.
Yes.
That's fine.
So all these quantities, which are the pre-activations on the first layer, are jointly Gaussian. So I can write the distribution, and I can express it in terms of a covariance. Okay, they're jointly Gaussian so far. Now the thing is, the pre-activation gets passed through the activation function. They're not Gaussian any longer. And if you take if you consider the output, what the output on the move pattern is W scalar sigma of the pre-activation, and you write the generating function. So you introduce a set as conjugate parameters. Say you compute the generating function of this. Then you come up with this quantity here, which is the conjugate of the outputs times the sigma. Now you're summing many over many sigma. And the idea is if the H's are completely uncorrelated, then there's a CLT result. But in general, they can be correlated because you have structure in your data set. Now there's a family of generalized central limit theorems. So this one is called Breuer-Measure theorem. There's a more generic, which is a Dubrovin measure, that give you sort of generalization when you sum nonlinear transformation under condition on the Hermita's function of the sigma, nonlinearity, and some condition on the covariance. So normally, if I sum quantities and they are weakly correlated, the sum is Gaussian. This is not true if they are correlated, but there are some condition on the stationarity of the C matrix. Okay, so it's if it's toplets basically, and some condition on the Hermit expansion of the first two Hermit coefficients of sigma, such that I can actually think that this sum here is Gaussian. This is the main point. When you do that, you just have to compute the covariance of that quantity there. That covariance is called now Q. It's the same as QS hat, but it lives in this replicated non-existent space because it's a QAB in a space which is going to be contracted to 0. I'm going to call this an order parameter, okay? Write all of this as a factorized form in e to the n something, and then take Laplace approximation. This is lie again. It's a 3-slide derivation, but what I get is the same expression as before. The 1 over beta plus qk to the -1. Again, you have the kernel, but now these kernels are replicated. You have a replicated, say, replicated green function, say, okay, and the replicated kernel. When you take n to the 0, in the end, what you get is that you have a certain number of these q's, which are the order parameters. I have to self-consistently determine these order parameters in terms of the maxima of this e to the n1s. And what I get is that this is the prior kernel on the source. If I train it infinite width, then everything is given by in terms of this guy. If I were to train KT all alone, everything would be given by this KT. But then you have this KST. So now this KST is expressing the similarity between the source and the target task and the level of the kernel. And this gives you a theory for what happens when you first train the source and then transfer. So
What is the KTE here?
oh, it's a kernel like this. So this is SK. So the covariance of the pre-activation in the source, you can have the KT covariance of the pre-activation in the target, and they are completely uncorrelated. Now what you get is a KS. The theory gives you a KST. So a joint kernel between the source and the task. And so you then compute the green function, the replicated green function, where you have KST inside, and then doing traces, you get expressions for the generalization error as a function of beta S, beta T, and gamma, possibly. Okay, so what this theory gives you is a compact expression for the generalization error as a function of beta S, beta T, alpha S, alpha T, gamma, and then you can plot this generalization error as a function of all these parameters.
So what is the expression for the generalization?
I'm not gonna show it. It's like it's an entire slide.
Okay.
Yeah, it's not nice.
Check that it actually works. The next slide. Yeah.
Next slide. Okay, so now I check whether it works or not. Okay, so we construct say a target source target couple. So we have a source task that comes from MNIST, and then target task, and then basically the network has to tell apart these guys from these guys. And as you can see, they're basically the same, but the E has been replaced by the F here, the J by the I. We do the same with cipher. We construct this correlated cipher data set, in which we lump together these guys, but then you see that we swapped some of the categories here. Did I actually? Yeah, so like this bolt is different than this one.
The dog
Yeah.
became a boat.
The dog became a boat,
The
yes.
car became a
Yes.
truck.
Okay, so you can think that there are some features here which are good to solve this problem. Now you give many pedals here and not so many pedals here and test it as a function of gamma. Gamma equal to 0 means no transfer. Gamma to infinity means I just use everything from the source. And then you plot it as a function of gamma. So this is theory versus data points. And these data points are very painful to get because you need to first perform a Langevin on the source. You need to sample from the source posterior. Then you take for any sample from the source posterior, you couple it to a target, and then you run Langevin on the target. So every point here is an average over many targets, averaged over the posterior on the source. So it's a lot of Langevin for each point. Okay. And this, as you can see, this is not data average in the sense you give me the source X and Y, the target S and Y, and I give you like a curve without you for you to train the actual network. Okay. So you can see that the curves are different and as a function of the data set. And so like in this case, you can go up to gamma to infinity. In this case, you have fine tuning, meaning that if I train from scratch, I get say 0.86, but retraining just a little bit, not going too far from the source, affords me a better generalization error than just transferring the entire source. This means I'm retraining from scratch, and this is kind of I'm close to the source, but not exactly at the source, right? Because gamma is not infinite.
So what is the difference for the data?
These are two data sets. Yeah, that's I think it's complicated. I mean, it comes from these. It must be some sort of kernel alignment between the Y's of YS and YT with this KST kernel. It's not so clear to me in the
Intuitively, I
spreadsheet.
would think, yeah, training on letters, their pre-training would help a lot because they're so similar. Whereas,
Yeah. Yeah, you should be. I mean, I don't have an intuitive explanation, whatever. But it has to be some sort of alignment of the dominant eigenvector of the KST kernel with the singular vectors of the KST kernel with the Y, S, and YT. So it's a complicated phenomenon.
So one of them is the letters and the other one is the
Cipher, yes. Letters and cipher.
Okay.
Yes. So the difference between the two
So
is
the number of data.
number data points, and also like we can like pre-process it or not. So I don't know if how long you guys want to. I can go very fast or
You have like 5-10 more minutes.
5-10 more minutes. Okay. I'll just tell you a little bit about this one. So this was the model I was talking about. This is a teacher student model. Now I'm being more precise here and telling you what the connection between the low dimensional and the high dimensional data set is. It's just I take the low dimensional times the matrix times sigma, and then you get the axis. And so you can control many things, but we chose to control the source target similarity by how many features you share between the inputs for the source and the inputs for the task, for the target. Okay, so you have a random matrix Fs, random matrix Ft. Some of the rows can be equal, some others can be completely reshuffled, and you can control the number of the ones that you regenerate, which is this guy row. Okay, so Ft is equal to F tilde with a certain probability row, and then with 1 minus row, I just use the ones from the source. And so we can play now with this parameter row, which gives us an explicit generative model for the source target similarity. And you can see that if row is 0.1, so you have 90% of common feature, it's always best to transfer. You're very close, the target is very close to the source task in terms of hidden features. Already at 50% of common feature, you have fine tuning. And then, okay, you can do it up to, say, 90%. At some point, you're going to see that this goes just up. So that means you don't have to transfer, okay? So the source, so these are the negative transfer efforts I was showing before, but in a different space. So the slide was like transfer versus random feature. This is transferring versus retraining. And you find that if the source and target task are different, then just retrain. And this kind of yes.
And where in the formula was actually the target distribution and the source distribution?
Yes.
I don't think I.
So
maybe even in the beginning when you like showed this generating function.
yes.
Where was there any term that was related to this?
So LS is a function of the whole data set.
Or
Right,
on the source?
On the source. And LT is a function of the whole data set of the target.
And then you implicitly assume that the data points you take there are from the target distribution.
Yes, yes.
Okay, so it was just basic in the index. Okay.
Yes.
Okay. I see.
I don't average over data sets. It's just I'm thinking there's a whole matrix of target inputs and source inputs. Okay, so this makes sense. The more the more similar source target task, the better it is to transfer. But then at some point there's a kind of a limit for this row, so that you don't want to transfer ever. Okay, so I think we come to the last slide, and it's connected to what you were saying at the beginning. So we can take this alpha going to 0, or take n1 going to infinity, and you go to the infinite width limit. Okay, so the color is indicating how many neurons you have in the first theta layer. So in the limit in which you have n1 going to infinity, you get that as a function of gamma, this guy is flat. This is a kernel limit in which the source doesn't learn anything, so there's nothing to transfer at all. And the interesting thing is that as you go down, now you start compressing the network. You can get that in general, a small, say, narrow network. Sorry, narrow network performs more poorly than a very large network. But then at some point, if you transfer it, then you get a crossover. There's a very interesting paper by Google where they show that basically infinite networks almost always outperform finite networks. But it's true for fully connected networks, but not for convolutional ones. So it seems that the renormalization, so in terms of this kernel framework, the kind of renormalization that the fully connected network give you is trivial. But the kernel renormalization in the convolutional case is more structured, so they can actually learn feature about like the similarity between the patches. So what this is telling you that in the infinite width, you're not learning anything, but then at some point you can beat the infinite width network with transfer, which affords you an effective regularization if you want. So you find the optimal weight of the first layer without doing hyperparameter optimization. It's like instead of doing hyperparameter optimization, because it's just one parameter, you pre-train. So you just train once instead of training many hyperparameters. Okay, I guess we're done. So some conclusion, we introduced this new framework to understand transfer learning in Bayesian neural networks. What it gives you is this joint source target kernels, and you can write the generalization error in terms of this KST sandwiched with YS and YT. And what we find is that, I mean, it's trivial in hindsight that target networks can outperform this best non-transfer predictor, which is the infinite width limit, the one which is better than all the narrow ones, but then at the same time doesn't actually learn anything in some sense in terms of feature learning. I think the most interesting part is the perspective, because so I did all this thing using this Broglie measure theorem, which is not there any longer, which is something that as a physicist I'm allowed to do. So I take a theorem, then I guess that someone in the future will prove generalization, plus some infield approximation. So it's kind of a Gaussian approximation, plus an infield approximation. I can write it recursively and get a recursive relation for transfer learning in a deep network in general. Okay, the equations are way more complicated. We're starting to solve them. So you can generalize all this theory easily. But with this mean field approximation, which is kind of important. So you need to have some sort of decorrelation between units as they go through layers. So what I was saying related to the Google paper, you can play all of this with the convolutional networks, and you get a more complicated renormalization of the kernel, which is local with respect to patches. So you have like this patch here in the image and this patch here. They renormalize in a different way. They basically have like a queue here and a queue here, and also a queue for their interaction. So you can find covariances between pieces of images that the fully connected network cannot do because it's kind of summing over all the image. Okay, so you can play all these EM convolutional networks and still have to do that, but I think this can be done for attention layer too. So the goal would be to generate the theory for LoRa or transfer learning ChatGPT. Now there's an interesting point, which is I think that this gamma coupling comes purely from a physics perspective, and it's in Bayesian setting. But what people like partition actually do when they fine tune is that they start from a certain configuration of WS and they train with the small learning rate. Is the small learning rate the same as having a certain gamma? And what's the mapping between these two? We still don't know, and I think it's interesting to look at it. And then this is correlated with what you were saying at the beginning. So what's alpha? The holy grail nowadays in the theory of deep learning for me is understanding one is the layer in the so-called quadratic regime, which is when P scales like n1 times n0. Because you have n1 times n0 number of parameters. When P is of the same order of number of parameters, then you start to saturate some information bound and you actually learn some feature. Here, basically, there are some papers showing that you learn an effective perceptron plus some noise. And you can calculate the effective noise, even in the deep case, by, say, using this Gaussian equivalence principle one layer after the other. But the theory for when now P is very large, when you have a lot of inputs, then it's very, very complicated. And nowadays, what we have is a Bayes optimal theory for a quadratic activation function, which has been worked out using methods from free probability. But the generalization to say any activation function is at the moment quite far. And it's, I think, a very interesting avenue for future work. And so, yeah, if you have any question, for now, I'm done.
If you have any questions, please.
Yes.
Yeah, very interesting work. So I'm from statistics, and so I relate your work to the work of Gunther Bartelt, for instance, who say, well, there's benign overfitting or not, so it can be beneficial or not. But the idea there is that they also related to linear versions or first layers. Is that you have a part that's a reasonable approximation, a low dimensional part, and then the rest is basically a way to hide some of the noise because
Yes,
the interpolation point into the flexible space that you hopefully have. So it depends a little on what other stuff as input you have in the target, input. And if that's reasonably independent, so that the rest of the space is takes up some volume, then that's possible. And my interpretation here is that you basically try to fill in exactly how does that space work.
Yeah, that's true, because this Q here, I mean, this Q is an effective regularization.
Yeah.
And it's basically the same. You can think of, say, the regularization theory in function norm, which will give you like an effective noise, which is like exactly this guy, but it comes from a different perspective. Yes.
Yeah.
But there's a strong similarity.
Yeah.
There's any questions? So we had a lot of questions during the talk.
Yeah.
And it's already time to eat, so maybe we thank you one more time. We can have more questions during the.
Yeah, sure. I'll be here until 5, I guess. So if you wanna discuss.